Alright, ladies and gentlemen, today we have lecture 1.6, Ionization Energy, one of the more important concepts in Unit 1. Let's get right to it. Remember, ladies and gentlemen, if you ever get concerned, if you ever get scared, just think like a proton and stay positive. I'm with you, alright? Let's walk right through it. I want you guys to think for a second. Here we have a dangerous robber, and over here we have this sweet dear old grandma. Now this sweet dear old grandma is holding onto her electron purse. Unfortunately, this robber over here is trying to jack her electron purse. Now in this case, the person who's going to get that purse is the one with the stronger pulling power. Whichever one has more power to pull the electron purse away. Now that might seem like a weird story, but it actually relates directly to what we're talking about today. Today's learning target is learning target 1.7. I can define ionization energy and explain how it relates to the charge of the nucleus and the electron. Furthermore, I can explain how this trend changes as you move throughout the periodic table. So let's talk. First thing you gotta know is a little bit about nuclear attraction. I think we all have a good idea of what happens with positives and negatives, right? When you see them together, positives, or things like protons, are attracted to negatives, or things like electrons. So what happens when you put these close to each other is they will try and move towards each other. They're attracted. The negatively charged electrons are attracted towards the positively charged nucleus, where all the protons are kept in there. The electrons out here feel the pull of this nucleus and the positive charges in the nucleus, and the more they feel that nucleus, the tighter they're held to the center. Now, why does that matter? Because it relates directly to what we're talking about. As you see here, we have the nucleus in the center, and we have electrons positioned that are in the inner orbitals closer to the nucleus. Those electrons feel the pull of the nucleus very strongly. However, the electrons outside them on some of the on the outer orbitals don't feel the pull of the nucleus as strongly. We're going to talk about why today. The concept of today's lesson is ionization energy. And ionization energy is essentially just the energy that's required to remove an electron from the outer orbital. So here we have a valence electron that is being pulled away. Now pulling that electron away requires some energy. The energy that is required to pull it away, we know as ionization energy. And it's a term you should write down and make sure you define it as well. It is green, so it is a vocab word. Now, if you look on a periodic table, you'll notice a couple things. As you move down the periodic table, the ionization energy decreases. It goes down. We'll talk about why in a second. Excuse my writing. It's poor. Decreases. I apologize. That's almost illegible. And as you move to the right, the ionization energy increases. It goes up. So the trend goes in this direction right here. The ionization energy gets stronger as you move up and to the right. So the ionization energy increases as you move to the top right corner of the periodic table. You can think of it like this. Elements at the top of the periodic table are strong. They have a high ionization energy. They can pull the electron purse away very easily, jacking. The old grandma elements, the ones that are really weak, are at the bottom. They decrease. As you go further south on the periodic table, they get weaker and their ionization energy decreases. Same thing if we look the other direction. As you move to the right, the strongest elements, the ones that hold on to their electrons the tightest, are on the right side, and the weakest ones, the grandma elements, are on the left. The reason why ionization energy decreases as you go down a group is essentially because you have your little nucleus and you have your electron shells. Now, as you move down the periodic table, the number of electron shells increases. So if you're at the top of the periodic table, you'll have elements with maybe only 2 electron shells, maybe only 3 electrons total. And you can see they're really not that far away from the nucleus. But as you move down the periodic table, you start to add more orbitals. The atom gets bigger and bigger and bigger. And as it gets bigger, it adds more electrons. And as you add more electrons, you start to decrease the power of the nucleus to pull on electrons in the outer orbitals. So say we have this electron out here. This nucleus has to go all the way out there just to pull on this electron of interest. And to do that, it has to reach through all these other electrons. Now, the fact that it has to reach through all these other electrons makes it weaker. And these electrons on the inside actually shield this outside electron from being held closer by the nucleus. And this is known as electron shielding. Valence electrons that become shielded from the positively charged nucleus as we add more orbits. That's why ionization energy decreases as you move down the periodic table. But how about the other way? Why when we move to the right? As you move to the right, you are adding more protons into your nucleus. So let's say we blow up our nucleus a little bit. We make it this big. Let's put 3 protons in there. 1, 2, 3. Which means we only have 3 electrons, which means 2 orbitals right here. Now, if I have 3 protons, that only has the force of 3 positives pulling in the electrons here. But what if I add 3 more? 1, 2, 3. Now, I have made this element 1, 2, 3. Now we're looking at carbon, which, as you notice, has more protons in the middle, making it stronger, but the electrons are the same distance away. So it actually pulls these in a little bit closer and holds them a little bit tighter, and it's a little harder to take them away. So their ionization energy increases. Let's try it out. So here, we're looking for the ionization energy from smallest to largest, and we're identifying potassium, cesium, and lithium in terms of their ionization energy and determining which one has the highest ionization energy and which one has the lowest ionization energy. So first, we have to look at a periodic table. So if we look at a periodic table, we see that we have cesium, potassium, and lithium. Let's draw those out. Cesium, potassium, and lithium. Now, since cesium is on the bottom, it is going to be the biggest, and the electrons are going to be the farthest away, so they're going to be the easiest to steal. Therefore, this is going to have the smallest ionization energy, and it will be our first element of choice. As we move up the periodic table, elements get smaller, stronger, and have a higher ionization energy. So potassium would be next, K, and lithium would be the largest. So I want you guys to give these next few problems a shot, see how you perform, see what you can do, make sure to use your periodic table at all chances. Here's what it looks like, pause it if you need to, and give these problems a shot. Order the elements from largest to smallest ionization energy: fluorine, carbon, oxygen. Order them from smallest to largest ionization energy: phosphorus, arsenic, and nitrogen. Summarize what we've learned today and test yourself on these 5 questions right here. I hope this helped, ladies and gentlemen. Take care.